John J. Hopfield is the Dickinson Professor of Chemistry and Biology, as well as a Professor of Physics at California Institute of Technology. Hopfield came to Caltech in 1980 from Princeton University, where he was Professor of Physics for 6 years. He received his PhD at Cornell University in 1958 and was a member of the technical staff of Bell Telephone Laboratories and a faculty member at UC Berkeley before joining Princeton. Hopfield's a member of the National Academy of Sciences and of the American Academy of Arts and Sciences. In 1969, he was recipient of the American Physical Society Oliver E. Buckley Award, prize in solid-state physics for his work in the interaction of light with solids. He is a 1983 winner of the MacArthur Foundation Prize Fellow Award. His current research involves an attempt to understand the relations between structure and function in biological systems, work that he considers a part of his original field, solid-state physics. His talk will concern the collectivities of neuronal networks. John?
Thank you, Ted. Having played bridge with you for so long as a graduate student, I know where your voice goes when you underline attempt. Because at any particular time, although all of biology can be described in physics in principle, many of the things which you'd like to tackle are actually too complex, and for many of the biological issues it simply does not pay to begin from the viewpoint of physics. I think that at the moment the time is right to try to make a kind of interconnection between parts of computer science and parts of neurobiology, and I think that the subject which helps you most in trying to make that interconnection are some of the insights one has from parts of condensed matter and statistical physics. What I'm going to do today is to try to describe some aspects of this three-way interface. Could I have the first slide, please? Do I begin them here? There we go. These are two of the computers that I use most often at Caltech. One of them my division chairman, the other one which sits on my desk. Each of these is in turn connected to a larger machine, the one to a VAX, the other to the provost. And these are both computers. They were both, the hardware was assembled in some particular way. A lot of the software is built into the way they came off the assembly line. Nevertheless, you can put new programs in them by hard work, and you put data in, decisions come out. I want to ask to what extent these act on the same principles and try to do that issue a bit. And the conventional way of asking how something works from the point of view of physics has been to go down and look at the microscopic details, and so you tend to head in this direction to take the cover off a box. Harry was not very cooperative. This is maybe not the best way to begin in computation. If you took the cover off a modern computer, you'd see all kinds of hardware. You took a cover off the IBM 703 or something like this in the late 50s, you'd find a completely different set of hardware, and as you pursued one down to the details, you'd study vacuum tubes, and the other down to the details, and you'd study silicon. And yet we know that these fundamentally compute in the same fashion. And so the much more interesting way to begin asking whether things are the same or different is to try to pursue them from the point of view of tasks. Here are two computational tasks. There must be just a fraction off the top of that. So never mind. The top is supposed to be a multiplication problem, a rather difficult one which I've long since forgotten how to do, and one which, even if you think of the cycle time of the human brain in some kind of reasonable terms, it simply does amazingly badly compared to what a digital machine does. The second problem is actually taken from the researches of the Bela Ulish, who will lecture later this morning. It's another problem, and I don't even have to describe the problem. As soon as that pattern went up, you instantly saw the plus sign in the middle of those C's, in the middle of that C of letters L. Not only do you do that fast, and your little microcomputer would do it very slowly, but also you fundamentally do that task in a different fashion. If I want to do this on a microcomputer, I go around and look at one object, look at another object, look at another object, and the length of time that it takes to find that line tends then to scale with the number of distracting L's that there are in the picture. On the other hand, you find that plus sign in a time which is essentially independent of whether there are half as many L's or twice as many L's. There really are relations between hardware and tasks, and the digital computer has been made to do the multiplication problem, and apparently you have been made to do another class of problems. There are other differences. One has to do with the reliance of computers on particular components. There is a great tendency when designing a computer not to put in a component without a purpose. Well, this doesn't sound strange. Of course, it costs money. On the other hand, biology doesn't have this general idea of purpose. It tends to add things in the development. If they overall somehow make this thing work a little bit better, evolution will tend to keep them. As a result, a biological computation must be done in a rather more holistic fashion than is computation in a digital computer. And this is particularly important because biological computers, when you get to a computer on the scale of your brain, are not made with precision, and yet they have to work. And so as you think about the issues, there are this Phil-soft aspect of the human brain, the parallelism of the human brain, and the sort of the holistic kinds of computation that it must do, which are rather different from the way that ordinary digital computers seem to work. The other difference has to do with some of the fundamental numbers involved. Human brain has on the scale of somewhere between 10 to the 10th and 10 to the 11th neurons or nerve cells. And each one of these makes on the scale of 1,000 connections with others. If you look at a microcomputer, it's much smaller on the scale of 1,000,000 gates. And the other thing which is very noticeable is that the number of connections per gate tends to be very small. The connections themselves in the biological system tend to be computing elements. And as a result, the scale of these two systems is just immensely different. Well, as you start to get computers which are larger in scale, they begin to look a little complicated. I mean, this is a typical modern microprocessor chip. This is actually a small one which was designed by one of the Caltech students. But if I give you the circuit diagram of this in complete detail and don't tell you how the system was designed to work, there are a huge number of ways that you could put inputs to the system, take outputs from it, program it to begin with by putting in sequences of bits, and it becomes virtually impossible to understand how to use such a thing unless you are given a set of instructions. Merely knowing the circuit diagram in complete detail is essentially not enough anymore. And this presents problems as one approaches a biological computer because you aren't ever going to know the circuit diagram in detail. And as a result, you must ask how you're going to make progress. One answer is slowly, and another is to make a virtue of what otherwise is the major problem, to try to make a virtue of the size of the system. Phil Anderson wrote a lovely article in Physics Today some years ago entitled "More is Different," simply reminding one that in all aspects of physics and everywhere else in life, when you got systems which had large numbers of, after you understood the science of how those objects worked in 2s and 3s and 4s, if you had 10 to the some large power of these objects, normally you'd have a system in which there was new physics resulting. And this or new science resulting, or new phenomena resulting, new collective phenomena. And this goes everything between, molecular collisions. Typical example, you can study collisions of two molecules in a large box, and after a while you get tired of that, so you put three molecules in the large box. And there's nothing in the collisions of 2s and 3s which directly suggests that if you put 10 to the 20th molecules in that box, sound waves will be a physical phenomenon. Sound waves rely on the collisions for their existence, and yet, in some sense, the essence of them is not captured by the physics of small numbers of molecules. Other areas, is a classic example of a collective phenomena. If you want to know why there are riots at some football games and not at Caltech football games, it has to do simply with the scale 10 people don't riot. Now I'm going to talk about neural modeling, and the model which I'm going to make of neurons is really going to be wrong in many details. One simply can't put in all the details. Not only aren't they known, but they're very complicated. You want to try to get the essence of the situation. And one important aspect of the idea of collective phenomena is the fact that collective phenomena can be relatively independent of the details of some of the things that go into them. For example, sound waves do depend for their existence on the collisions between molecules. And yet the formula which you checked freshman physics class on the velocity of sound in various gases didn't even contain a description of what those collisions were. And so although the phenomenon essentially involves the collisions, the details don't matter a great deal. Essentially all solids melt to liquids. The melting temperature, the melting entropy, and so on depend on the details, but the fact that you have a melting phenomenon is universal and doesn't really depend upon the detailed nature of the molecule-molecule interactions. And in that same sense, we can hope, if we're looking for collective properties in neural systems, to have a robustness of our insights which will go beyond the fact that some of the details of the model must inevitably be wrong. So I'm going then to pursue the thesis that there ought to be collective effects in neural systems. Neural systems are computational systems. One would wonder then whether the effects could be of computational interest. And to investigate that, I'm going to pursue the particular computational question of memory. Now, one of the most striking things in biology is that memories are entities. They have a way of sticking together. The caption of this reads, "I'd like to advise you in this matter, Morton, but there seems to be nothing left in the old noggin but former girlfriends' telephone numbers." Now, he's got a telephone number which is going to have lots of digits and probably write a face, a name. Even in the failing state of his CPU, those memories hold together. Well, that's not a problem in a conventional computer architecture. Conventional computer architecture basically stores memories of such things in this kind of analogy. You have a huge building, as it were, a huge library, all the data which you want to keep about one thing, in some sense, in a location, and for simplicity you tend to put it in that location together. And there's just no question of memories mixing, because the information about something is put some particular place and information about something else is put elsewhere. Now, there's no question about memories mixing. On the other hand, this kind of architecture leads to the necessity of knowing the address at which the information is stored in order to retrieve it. This also has local information storage, local in the sense that one particular place is used to store a particular thing, and if you then destroy that particular place in the computer, a particular thing is forgotten. And one would suspect that the biological memory is a little bit more holographic in nature, in the sense that one would believe that particular parts of the hardware are probably participating in several memories, and memories really then tend to overlap within the hardware. That creates problems of how do you keep memories apart. And the problem of content addressability also is a major one. The idea of content addressability is very simple, or associative memory. You have a memory which has many blocks of information in it. And the way your memories function, it's certainly true that if you're given a particular experience, if I remind you of one aspect of it, you can recall all the other aspects. And it doesn't matter which aspect I pick to remind you of, you can still reconstruct the whole memory. The memory is addressable by content and not by location. Now, kind of thing can be built in computer hardware, can be built in computer software, but it's rather awkward to do. See, the difficulty is, you know, if I want to store information about people, I write little lists of things, and I tuck them away in some fashion in a book or in a catalog. Now, if I put them away in alphabetical fashion, it's very easy to find the people if I'm trying to recall them by name. But if I'm trying to recall them by other information, then I have to have some kind of index. And if I'm trying to recall them by information which might take about 3 of those items, each of which is a very soft, weak item, and make an index so that I could find this person in a list of 10,000 people on the basis of 3 or 4 of those soft items, the problem of indexing it just absolutely gets out of bounds. It grows exponentially, particularly if you're interested in making a memory which can deal with input cues which are not necessarily accurate. Well, the idea of content addressability sounds very much as though you're going straight toward computer science. I'd now like to just point out that the essential idea of content addressable memory is something that physical systems can have spontaneously without plan. And to do that, I'd like to point out the essence of content addressability from the point of view of mathematics. Suppose I tried to remember 2-letter combinations. So I've written the alphabet on each axis, and any particular 2-letter combination then is a point in that space. And I could have 2 memories, he and am, which are just 2 points in that space, and I could say, those are the things I want to remember. If you have a content addressable memory, what we would like is if you are given the clue H, the system would then arrive at the point HE, and you have the information about that memory. Or if you were given some more ambiguous thing like the letter combination GF, a content addressable memory should realize, oh, that's much nearer HE than AM. And so it would start from the coordinate GF, the initial clue, and it should move over to that nearby memory point, HE, and produce that memory from the clue. If you continue this on, you find that in an abstract fashion, the essence of content addressable memory is a system which has some dynamics, a system which, as far as its change in state space with time, could be described as having a flow. And if you think of the memories as the point where the x's are in this state space, those are stable points of the flow. Locally, the flow goes to that region. And as a result, start from some place with partial information about where a memory is. The system will go on and reconstruct the memory exactly. Whereas if the partial information you have is more like some other memory, it will go and reconstruct this other memory. But the idea of content addressable memory is contained in such a picture. And since you know that there are many physical systems which have multi-stable points, that is, which have many stable points in their dynamics, you realize that there must be sort of simple physical systems which could function as content addressable memories. And these content addressable memories are things which you really would very much like to have. Most workers in artificial intelligence, for example, will claim that if you could only make large content addressable memories, you could make much more progress in artificial intelligence if you're trying to get things to do human tasks. The primary things which humans seem to rely on is a big grab bag of associative or content addressable memory. To go further than this, we must go back now to the question of what neurons are like. We must try to get the mathematical or the physical essence of what neurons are doing as they do their calculations or go through their particular actions in a brain. Well, first of all, neurons are looking pretty grim. This is a slide taken from a drawing of Cajal made about 90 years ago. You can stain a section of brain tissue with a stain which stains essentially completely about 1% of the cells. And so you can see a cell body and its processes going out and other little things going on. And there are many other cells making connections with this one through all these interconnection networks. All the wiry things you see are the interconnection networks. And just as in integrated circuits, the brain actually tends to fill up with wires. Of course, you can see this because most of the cells aren't stained, and you can see how all the high connectivity is maintained. And you can also get the impression that you are just never going to, if each time you make a slice of what is nominally the same animal, you find something which is developmentally different, you'll just never know the real hardware. But this is what the hardware, roughly speaking, looks like. Functionally, you make measurements in electrophysiology, putting an electrode into one of these cells and measuring the potential difference between the inside and the outside. And the next slide shows the potential difference as a function of time recorded one particular cell in the cerebral cortex of a cat. And this particular cell is one in the sensory cortex, which is indirectly connected back to a touch sensor on the lip of the cat. And if you look at the potential as a function of time, there's a noise level, and then every once in a while there's one of these spikes. These spikes last a period of time, which is about a millisecond. And if you're not stimulating the lip in particular, you get a background level of those spikes. When the lip is gently stimulated, then suddenly you just get a dense thicket of those spikes. Here's another stimulus, which is somewhat different, and you can see that you go from relatively few spikes per unit time to many more spikes per unit time. For many purposes, you could try to approximate the kind of behavior that this represents by saying that a particular neuron has essentially an input-output relation, which might be described in the following way. You could take, along the y-axis, a short-term average firing rate, average rate of spike production of the cell, as a measure of the output. And the potential that you're holding the membrane at, the mean potential, as the level of input. And the cells go from, on the one hand, the potential is large and negative, they simply don't produce any output, to a saturating output, and they follow a curve which was roughly like this black curve. This suppresses all the details of that spiking behavior and replaces it by an average behavior. This is only approximately valid. It's rather like, I believe, it's trying to say, well, look, the system is really quantized, but let's look at a more classical representation of it. Now, if you take this as the input-output relation, you want to know what with it next. There are two obvious approximations. One is to approximate it in a linear fashion, and the other is to approximate it as a step going between two threshold levels. The linear way is not perhaps the most useful way of doing it. If I suddenly turn the lights out in the room and I say, go for the nearest exit, and you're sitting there in front, nearest exit, well, there was one on my right and one on my left. A linear system would then proceed to walk straight through the center of the wall. Linear systems take averages. And the essence of computation is making decisions. When there's ambiguity, you do not want to recall the average telephone number of old girlfriends. You want to recall one or another. So I'm going to take this on-off characteristic. We've also done some modeling with the more nearly real characteristic, but I'm not going to get into that. Now, the next thing which you have to put in is something in the dynamics, because the whole essence of the system was described as this flow in state space. So you have to have a time dynamics. And the entire algorithm I'm going to have for this system is really very simple. it says that any particular neuron is either at the moment off or on, that it had a low value or a high value of its output. And what its state is going to be controlled, first of all, by its input. It has an input described in terms of a sum over all the connections that are made from it to it from other neurons, multiplied by a Vj, which is 0 or 1, depending thank you, Ted. Depending on whether the other neuron is off or on. So this is the input to a particular neuron. And the algorithm, the time algorithm I'm going to take, is that each neuron adjusts its state, turns itself on or turns itself off, stochastically in time. At random times, it pokes its head up, asks, should I be on, should I be off, and readjusts itself. And simply does this according to a threshold law, depending upon whether the input, total input to it, is greater than or less than 0, and that the different neurons go ahead and do their processing asynchronously. This then describes an algorithm by which you can see how the neurons will change their state as long as you already have a description of their connections. And one of the first things which you would like to know is this algorithm the kind of thing which has a flow of this sort with nice stable points, and you tend to go to stable points, or does it have some much less useful flow? Does it have a chaotic flow, or does it go in huge limit cycles? And it turns out that under a wide class of circumstances, the algorithm actually has a flow of this sort and moves toward stable limit points. The next question which you'd like to know is why, and the simplest representation of why comes from the idea of a spin glass. Everybody remembers what a ferromagnet is, their exchange interactions between spins, and as a result, spins like, say, to be parallel, and you get a magnetic phase transition, which is a collective phenomenon and very stable at low temperatures. Or you can have exchange of negative sign, and you can have antiferromagnetic structures which are stable. Or, in a subject which has been being studied for about the last 12 years now, you can have a spin glass, a system in which the exchange interactions between different spins are of a much more random character. That system, too, at temperatures, has stable magnetic states. But unlike the ferromagnet, which tends to have only a few stable directions of putting its magnetism, the spin glass turns out to have a huge number of stable ground states. It has many ground states. There's a phenomenon known as frustration, which occurs in that system, which says that no matter how hard you try, you cannot make the exchange between all of the spins happy in trying to minimize the energy of the system. It turns out that there is a transformation between this kind of idea and the algorithm that I described to you for the neurons, such that the essential reason that the neuronal system, the model neuronal system I had, has stable states is very much related to the fact that the spin glass has stable states, and the reasons what the algorithm for changing the neuronal state does is essentially provide an algorithm which tends to move this energy downhill all the time, and thus aha. All right. Now, downhill all the time, and that's why it converges. Now, there is in this system, let me just illustrate in a, good. So really behind the flow map, which I've already given you a picture of, there really is an energy terrain. And the reason the system converges is it's going downhill, tending to go downhill in this energy terrain. To put it in less abstract terms, or more abstract, depending on which way you think about things, you can take a model with certain memories in it. There is an algorithm for choosing the connections so that particular things will store it. I'll show you that algorithm in a minute. But this system of neurons actually has some memories stored in it This is one of the memory patterns it has stored. Every place there's a blank, there's a 0, and every place there's an X, there's a 1. It had 5 such patterns stored. And if you start from this particular state, which is nominally stored, it's stored, you see, in the connections. It's not stored in the state itself, but it's stored in the connection pattern, or the Tij matrix. If you take this nominal state, and instead of starting the system with that state, you take this state and flip some of the bits. So you make a state which is sort of like this, but it's got quite a few mistakes in it, this one. The algorithm then proceeds, and through time, the system will finally come to an equilibrium state, which is the actual state that this starting state was most. Or if you want to do this less abstractly, you can, there's a system in which I've taken the same kind of network and coded into the bits telephone numbers. If I now take one of the particular telephone numbers which is remembered and take 3 arbitrary digits and make them agree with one of these telephone numbers and take the other arbitrary other digits here and choose them arbitrarily, this is enough information that the system started from this state and left to its own devices converges to that telephone number, which it should. There's enough information there that it should have been able to select it. The system, as I've described it so far, is a forced choice system, but it doesn't have to be a forced choice system. There are other things that you can do with the system. One of the clear distinctions between what you do under 2 different circumstances has to do with whether you are forced choice or not. If I speak of difficulties, if I have had a horrible accent in English anyway, you will have understood that I spoke really of the word difficulty, but I just put the accent in the wrong place. On the other hand, at the moment, you probably will have actually rejected difficulty as a word because you would have expected me to pronounce it correctly. In the state space flow, the system that I've described so far has a state space, and the flow is divided up in such a way that no matter where you start, you are forced to go to one of the memories that you already have in the system. It will take any input state and attempt to classify it into one of the memories that it has. Well, by the example in English I just described to you, you operate English in a regime like this. If you start with a sound which is sufficiently like a word, you will believe that that word was spoken. But if you start with a sound which is too far away from any word, the state space represented here, you will not find a word that is most like, you will simply reject that as a word. And the difference between operating in this regime, where things which are adequate fits are picked out and other things are rejected as unfamiliar, turns out to be simply a question of taking the system that I've already described to you and running it at a threshold which is finite rather than at a threshold which is 0. I promised to tell you something about how it is that you put memories into this system. If you want, this is now written in terms of μ's, think in terms of Ising spins, because it's the simplest way from the point of view of physics to try to understand what's going on. What you want to do is to be able to put a system which already has memorized some things, and you want to be able to install another memory into the system. The correct prescription for installing another memory into the system is to change the connection strength between neurons I and neurons J according to the value of the product of the spin or the state of neuron I and the state of neuron J in the new memory that you're putting in. So one simply increments Tij this way. This operation does a good job of making this new state a new stable state of the system and does not at the same time destroy the old memory states which were present. This idea you can try to put into having continuous learning. So you can try to go make the dynamics now a little richer by having a system which actually learns. a system which has inputs to the cells, or inputs to the, or bias fields to the spins, if you want to think about it in a spin example, coming from the outside, and Tij, the connection matrix itself, could continuously vary in time in such a fashion. You need to do something, incidentally, to keep the Tij matrix from saturating in various ways. But if you do this, you see, it will produce changes of this nature. This is the kind of thing that you have to do to remember new things coming into you from the outside. And one of the things which this system has, as soon as you try to do this kind of thing, is an ability to remember things being told what a category is. Simply, if its inputs, suppose that we're trying to remember faces. If its input looked like one face for a while, then looked like a very different face, and then looked like a very different face, sequentially in time, each one of these coming for a while, this model would actually increment in such a way that the individual faces would be remembered. You'd never have to tell it, this was one face, now we're changing faces, this is another face. On the other hand, if you get things which are quite similar occurring for a while, for example, there's a face there, but it's moving around a bit, this algorithm will spontaneously just change the matrix, and what it does is to actually construct something in the way of categories as a result of the way that it's outside, that the outside world changes. Now, I've been on learning in this system, kind of system, for about a year and a half now. There are certain problems having to do, oh, that doesn't have it, sorry. There are certain problems having to do with controlling learning. There is a great tendency of this kind of system, in the presence of sensory deprivation, to look at itself, say, oh, I am in the best possible of internal states, and learn that state so thoroughly that it squeezes out all other memories. Sensory deprivation, in short, is bad even for these networks. Now, I've described this in terms of a stochastic algorithm, in terms of pseudo-neuron hardware. But there's no reason that this system actually could not be made to work in this kind of fashion. And John Lamb at JPL has actually made a small circuit of this sort with operational amplifiers for neurons, no stochasticism at all, with read in here for the Tij matrix. And this kind of system has multi-stable states which are determined by the resisted network in a way which follows immediately from the way that the multi-stable states of the spin system were determined from that network. And this kind of system, just left to run as an analog, as a fully analog system, if you start it with these op-amps, some of them set like one of the memories, but others set in a way which conflicts with it, the system will go and fix up the op-amps which are set wrong when you let it free and run. In short, this system really does, in a completely analog fashion, operate correctly as a content addressable memory. It would be nice to try to make this kind of thing in real hardware. What you want have such a thing is to be able to have resistive elements here which are changeable as a result of the time history of the voltage difference on the two leads going into that resistive element. You'd like to have a resistive element which, if you put a high bias across it, changes the resistance in a reversible fashion, and then read the neuronal state of the thing by running this whole circuit in the low voltage regime. You notice, incidentally, how easy it is in principle to write a memory into this system. Writing a memory into the system can be done massively in parallel. To write, what you do is to hold voltages 1 or -1 on those lines and on these lines. Then each of these intersections has the information it needs to know how to readjust itself, because each of these readjustments for a new memory depended only on the value of that neuron and that neuron reset that resistor. In short, you don't need to know anything global about the memories in order to understand how to install them, in spite of the fact that the memories are not being locally installed. And I said the memories aren't being locally installed, and that each memory is actually spread out over the entire matrix of connections. And the redundancy is such that if you take out 5%, you simply shoot out 5% of these connections. There's a little bit more noise in trying to determine memories, but no particular memory fails. And so this system really does, you can see in these shoot-out experiments on a computer, that it does actually operate in a holistic and non-local fashion, and it spontaneously has this fail-soft mode. Well, let me try to summarize. First, with respect to biology. I would reluctantly admit that with respect to biology, the situation is roughly like this. This box says theories, this one says proofs. On the other hand, it's very hard to see how else you can get a system which is as imprecisely made and as noisily functioning as a system of neurons to work if you don't try to make some use of its collective behaviors. Because we can see that, at least in the models, these collective behaviors come forth in a very simple way. It doesn't take much in the way of model details to produce them. And you can see that the system, just this very simple system, spontaneously has the property that you would have thought to begin with you'd have to design, namely a content addressable memory. And you can take this same kind of hardware and approach other biological tasks. Some of the other things which you can do are, among them, is to get it to learn time sequences rather than just stable states. I also think you ought to be able to, as I remarked, actually to use this technology in a silicon-like system, richly interconnected, to make large content addressable memories of a sort which are parallel writable and of a sort which could be made to find their own categories. But I believe, finally, that there are aspects of higher cognitive behavior which emerge directly from simple properties of cells because of the large numbers of cells and the large connectivity of them, and that such properties don't have to be meticulously planned. And I think, finally, that both conventional computers and neurobiology have much to gain by considering the subject of each in the light of what is known about the other, and that the bridge between them is really statistical physics and the spin glass. Thank you.
Are there any questions? Yes.
How much beyond your typical microcomputer do you think you have to go before you get something that would show some of the characteristics of
We've done a lot of modeling of this on VAXs with up to 1,000 neurons. You need something on the scale of 30 flip-flops or operational amplifier equivalents neurons with something on the scale of 1,000 connections between them for the collective properties to come out and start dominating. Things beyond that size very nicely display collective properties in all the simulations. And you can already in the analog systems begin to see the collective effects with numbers with 10. But the use really is if you try to make larger systems because you have all the parallelism going for you, and you have the fail-soft nature of the not needing all the connections to be right.
You imply that the system is sort of thermodynamically stable in this configuration. Do you also find circumstances in which you get more chaotic behavior? Or
Yes. Yes. The key to thermodynamic stability is you have a connection matrix which is symmetric. I is connected to J, J is connected back to I. If you make the system so that that is no longer true, you can get much richer classes of behavior, including sequence generation, but including limit cycles and chaotic behavior also. So there's a trade-off there. The more you move toward non-symmetric matrices, the more interesting things, and the more you lose statistical control of the situation.
Does your model allow for differences between short-term and long-term memory?
all memories in this are embedded in the connection matrix, the Tij. Now you have probably three kinds of memory. You have very short-term memory, which is sort of the electrical reverberation, and the kind of thing which, if you're just hit lightly over the head, you lose the last few seconds of activity. That's electrical. Then you have some shorter-term and longer-term things which are believed probably to be changes in the connections. I haven't described the mechanism by which those Tijs are to be changed. Your medium-term and your long-term memory, though, would both be viewed as being embedded in those Tijs, and the real, true short-term memory I haven't addressed.
If instead of focusing on the neurons, which are large and extended, you look at the connections or synapses between them, call them the gates, and then identify those gates which are close enough to one another that they together start or don't start a pulse propagating. Does the connectivity of the gates defined that way look all that different from what you find in electronic computers?
Nobody is able really to look at the signal, basically the signal propagation, down in this arborization of the wires. You tend to have, there's this tree structure, there's a connection here, a connection there, a connection there. No particular connection is thought to drive that whole cell. So it takes something on the scale, one would believe, of tens of connections to do it. But it may be that if you go and look out in the arborization, the numbers might be 10. But the system, clearly from the statistical point of view, is going to be very noisy if you get down to things like that. And it wouldn't surprise me then if it actually relies on numbers which are larger than that, just because you've got to do the statistics, but not known.
Thank you very much.